So this should work right now.
Yes.
Excellent. All right, so thank you very much for having me. And I will be presenting with my co-presenter, Ryan Coffey, who is also online right now. So thank you very much. Today we'll be talking about something slightly different. So we're going to be talking about using machine learning, but at the edge of our network and using it in real time. So the reason we want to do that is we're going to want to apply this at several places, including at SLAC for the LCLS2. So for the last decade, we've had LCLS1 running, and what this is we're using the existing copper accelerator to accelerate bunches of electrons, which then go through the undulator and they emit very powerful X-rays, which we can use then to image molecules and do all sorts of experiments. Currently, we've been upgraded to a new superconducting accelerator. So the copper accelerator, the existing one, ran at 120 hertz, so 120 shots per second. The new superconducting one will be a lot brighter. It will be 10,000 times brighter, and would also run at a continuous 1 megahertz beam rate. So we are going to have 1 million shots per second, which means all of the instruments, if we want to make full use of this, we are going to need instruments that are able to acquire data 1 million times per second. So we have a huge real-time data challenge on our hands. So we have several different experiments that are going to be running, and I'm not going to go through them, but the important numbers here for us is that we are going to try and collect for different experiments 20 to 1,200 gigabytes per second for a single experiment. So we have a lot of data to collect. This is not the only field or experiment that has a huge data collection. So of course, everybody's familiar with the LHC. The LHC has a significant amount of data nodes just to collect data, and they still have to throw out a significant amount just because they can't quite keep up with all the data that's coming in. The Future Circular Collider will be even a worse problem in terms of data management. And if we go more with the theme of this conference, the dark matter and neutrino experiments will also be generating more and more data as the new versions and the evolution of the experiments continues. Another huge issue for data right now is also in medical imaging, where the density of data creation is hitting pretty high rates. And also, if we go out of the field of science, if we go into the industry, industry also has more and more sensors going on, and they all need to collect data at the edge and then transfer them to a central. So there's more and more data moving around. So we want to try and find a solution to actually reduce that data, because that data does cause issues and does have drawbacks. So for one, it has a huge economical and environmental impact. If we have more data, we're actually going to need more power to transmit that data. For the Future Circular Collider, they actually project 2 megawatts just for the links. No compute, no powering the detectors. This is just transceivers. So that's a huge amount of power necessary to move around raw data. We need to move those on fibers to the data acquisition system, and that adds costs. And of course, it also adds a cost in space. So we need to find some place to put those fibers. More storage hardware, because we need to save that data somewhere, but that also means that we're going to need to power the data centers where that's stored. We're going to need people for those data centers, and we are also going to end up with huge data sets, and huge data sets, when it comes time to do the data mining, we're going to need people to do that data mining. We need more power to compute, the bigger the data set is. So you can see that we're really creating here a whole chain just because we are saving a lot of data. So we want to try and focus more on the meaningful information that is in that data, so that we don't drown and end up losing data just because we don't have time to get around to dealing with it. So how we want to do that is that we want to do some real-time data reduction at the edge, so as close as to the detector or wherever the data is generated. So this is a standard data acquisition chain where we have a detector, we have a DAC system, which is ASIC, FPGAs, And that data is digitized and sent to online analysis nodes, which can do some data reduction online, and then that's saved to disk. We propose to add, we want to, the reason we want to change this is that if we assume that we're running at 1 terabyte per second at LCLS2 for a 12-hour shift, nonstop. Now I know that we rarely take data nonstop, but just for the ease of the computation, this is going to create actually 43,200 terabytes per shift. And that's equivalent to 56 years of 4K movies, nonstop. So no sleep, no eating. That's a lot of data to deal with. And all that data also adds costs to the storage. So that's $1.3 million per month of storage costs that would be created every shift. Now, of course, there's some assumptions in those numbers and there's some variations, but it's still big numbers. So what we propose is to replace the data acquisition part with an edge ML. So putting some machine learning at the edge that is going to analyze and reduce the data in a smart way before sending it on to the online analysis nodes. So this is going to do some data compression, data reduction, data vetoing right at the edge. That also gives us more options when it comes to giving feedback to the detector, so we can adapt some detector parameters for the current experiment. It also gives us options to send information to the source to change how it's working. And it gives us the option to give some feed forward information to the online analysis nodes to say, hey, this particular event, we should use the complicated algorithm, and that other event, we should probably use a simpler one because the events have different characteristics. So to prove that this is actually a good approach, we actually tried to apply it to the cookie box, and I'm going to have my co-presenter here present the cookie box.
Hi, so Ryan Coffey. We use this, it's called the cookie box for historical reasons, for what it reminded its originator of. But the idea is that we have at least 16 sensors arranged around a circle. And each sensor is measuring the time of flight for photoelectrons that get ejected from noble gas atoms that are by the X-rays. The whole thing happens inside of an optical laser field that is circularly polarized. So we're going to produce an outgoing packet of electrons with a momentum that is just the difference of the X-rays over the ionization potential. And then what the optical laser field does, kind of indicated over on the left by the circular arrows, it sort of shifts this momentum distribution away from the origin, away from 0, 0 in this picture right here. I think the animation, there you go, shifts it according to the time. And so the circular polarization makes one cycle around the clock every 3 femtoseconds if we're using a standard laser. But we can change the wavelength of the optical laser in order to effectively change the rate that the clock hand spins around the clock. And so this gives us the time of that particular photoionization event. And then based on the shape of this, are the lobes oriented like this or are they oriented like that? That can give you the polarization of that particular photoionization X-rays, because the polarization determines the direction, the principal direction of the ionization. And so I can tell if it's linear horizontal, linear vertical. And in fact, I'm doing this for each of the sub-pulses within this overall X-ray pulse. So if I have multiple pulses, I get the independent polarization from each of those. And then also, let's see, so that's the number of pulses that we have in each shot. Now, it's not just that I'm counting the number of pulses in their polarization, but based on how open these circles, shifted circles are, that tells me the energy of that particular piece of the X-ray spectrum that produced that feature. So I get the energy. And of course, because of its location around the circle, I get the relative time of that spectral component. So I'm getting what's called sort of a time energy spectrum or spectrogram of each X-ray event. So an X-ray event composes this lower right-hand corner of something fairly complicated for these free electron lasers. One of the early jokes was, is a free electron laser actually a laser? And being originally a laser guy, I would have said, no, it's a glorified flashlight. It's not really all that coherent. They're pretty ugly pulses. However, one of the more recent methods is akin to tachography. If you actually know what the complicated shape of this X-ray pulse is, you can do more of a statistical interpretation of your data and get super resolution in spectrum or time. And so that's sort of why we're so concerned about knowing the shape of this X-ray pulse, fairly complicated pulse. Okay. And so our goal for this has been to use this device, the cookie box, which can give us the time energy distribution of an individual single shot of the FEL. Use that for adjusting the downstream actions. So like Audrey said, if the pulse is sort of abhorrently pathologically complicated, maybe we just throw that shot away. But if it's reasonably interpretable, then we can apply a statistical analysis. Or if it's just a single subspike, well, that's attosecond spectroscopy, which is pretty hot right now. And if it's two subspikes, that's attosecond pump probe spectroscopy. So essentially, we're routing the data according to these early control decisions into styles of analysis. And that's why we want this to happen early on. Because like Audrey had said, we want to get as much of this analysis done as early as possible. So we're not transferring raw data, we're transferring physically meaningful data. And again, in the early days of LCLS2, that's going to be at 10 to 30 kilohertz. So we need to get our job done in less than 100 microseconds. That's sort of the goal that we set for ourselves. And so the concept for addressing this goal is the waveforms for each of these 16 detectors around the circle are fairly complicated, but really they just evaluate to the time of an electron that hits on a time of flight detector. So from this upper left, we can effectively convert into 16 different sample points in angle over the 2 pi for the energy, because we have a time to energy conversion that we will also implement in the upstream FPGA. Now, once we've got that energy conversion, we get this funny sinogram. And from the sinogram, you can see, oh, that's a nice single spike. So this is good attosecond pulse, easy to analyze. I throw this into the attosecond spectroscopy bucket. And now that's a simple compress and save, because since it's attoseconds, I don't need to save the full spectrum. I just need its width and its centroid, really. And that tells me in the time energy domain. And so I can really reduce this entire 16. This detector itself is on the scale of up to the terabyte per second rate if we stored the raw data. But we're not going to. Like I said, for this simple case, we only need like 3 numbers to classify every other downstream decision. Now, that's not always the case. That will be probably some smallish percentage of shots will be this simple compress and save case. When we move on to the next, it's a fairly more complicated thing. It's a sinogram again, but it's sort of an additive sinogram. And so now you see something that looks a little wonky. And a little wonky means that it's a rather complicated pulse. And so this is the kind of thing that if it's reasonably simple, we can retrieve it. And then we can do one of these sort of tachographic, time domain tachographic reconstructions for super resolution. But it does mean that we need to treat this waveform with a more advanced reconstruction. And so this will probably be a bigger model that will try to do this inversion. And whether we choose to apply that advanced reconstruction is based on these early decisions that have to happen within that first handful of microseconds. Okay.
Awesome, thanks. I'll take over again to see how we're actually going to do that, because now 100 microseconds is pretty short time to make that decision. So we're gonna use a neural network. So the inverse reconstruction problem is actually pretty complex. So we're using a neural network to actually do the analysis in a faster way. And the way we are going to train this neural network is that we're going to generate various X-ray shots that have all these different wonky pulses inside them. And we're going to simulate how the cookie box is going to behave and get the MCP signals out of that. We're going to do our signal processing as we expect it to happen. And then we're going to use the output of that to train the neural network, and we can compare with our ground truth to do our training. How does this look in the physical hardware? We have our circular MCPs, which are around here. So we actually have 16 in our, well, we can have up to 16 in our actual final cookie box. I just put 8 here because I wanted to not overload the slide. Each of these MCPs goes into a digitizer, and each pair of digitizers goes into a first FPGA, and that first FPGA will do our data pre-processing. That data is then sent to the central FPGA, which collects all 16 data streams, and we'll do host our neural network that takes our decisions on what we were going to do with the specific shot that we got. Now, we need to run very fast, so we built an architecture that is going to run very fast. So our neural network is going to actually be entirely unrolled, where each neuron is going to have its own physical implementation. And that means that when our shot comes in, it's going to move as one into our first layer. Once it finishes computing and our second shot is ready, the first shot is going to go in the second layer, and the second shot is going to go in the first layer. And then when the third shot comes in and the first layer finishes, everybody continues moving that way, which means our entire process is going to be pipelined, and we're going to be able to calculate several shots at a time. At the end, we're going to get whether we need the simple reconstruction, the advanced reconstruction, or we hope to actually put in a way to detect the anomaly. So it's not fitting either of our models. So let's do something different with the data.
5-minute warning.
Thank you. So we have an entirely parallel calculation happening for each neuron and a pipeline process for each shot. Now, the way the FPGA, it's implemented in the FPGA is that we, our center piece is the digital signal processor, the DSP unit. So we have some FPGAs that have several thousand of these. They have the multiply and accumulate function inside, which is very useful for neurons. And we have our activation function, which will be either implemented as a calculation or as a lookup table, depending how complicated our activation function is. What's interesting here is that our weights and biases are in RAM, so we can actually update the weights without flashing the hardware. However, we can't change the architecture. We have to flash new firmware to get a new architecture. But we can update the weights as often as we want. So the first question we asked our neural net is how many pulses is in the shot? So how complicated is the shot in time? So we can have 1 shot or 2 shots, and then sometimes we're going to have 3 or something very messy, or something we actually don't even get a pulse in the shot. It's just we didn't get any light, or we got very little light. So we're going to classify these for the simple compress and save or for an advanced reconstruction, and we can just veto the ones that don't have shots. So we trained a very simple neural net with only 3 full layers. And the results here, we have the true label on the vertical axis and the prediction at the top. And this is our confusion matrix if everything went well, but of course it didn't. So we have some confusion. It's very good at detecting when there's no laser, no X-rays, but it's less good at detecting complicated shots versus 3 shots. But that doesn't really matter because both of them will be sent to the advanced reconstruction. What is problematic is where it's confused between 2 shots and 3 shots, because that doesn't go to the same place. So there's still some work to be done on this particular neural network, but our goal was to demonstrate that it actually ran on an FPGA very fast. So the first thing we did is confirm that it works on the FPGA, and it gives us the same results. So we took a data set of 10,000, sent it in the GPU, and got the labels from the GPU, and then did the same thing with the architecture that's on the FPGA and compared them, and we have 100% match, so we have the exact same functionality. Now, the moment of truth, how fast did it run? And we measured that it ran under 20 microseconds. So within 20 microseconds, we have an answer about whether the shot, how many pulses were in the single shot. This is for a 62.5 megahertz clock, but we hope to be able to crank up the clock up to 250, where it would be under 5 microseconds. Now, latency is not the entire story. We also need to be able to run a lot of shots per second. So how many shots per second can we compute? The limitation is the longest latency per layer. So our longest layer is layer 1, which has 800 inputs, and that means we can run to 77 kilohertz, which is above our 10 kilohertz to 30 kilohertz that we're aiming for at the beginning, but it's still under the 1 megahertz that eventually we're going to reach, so there's still some work to be done here. So the next steps for this neural net is, of course, improving it, and we're going to also increase the network complexity. So we're going to try to get the polarization out, and we're going to need to get that energy spectrum out for the complex shots and the temporal pulse sequence. And we want to input our anomaly detection, our confidence about what type of pulse it is. We're going to deploy that for the LCLS2 cookie box, and eventually improve the event analysis rate to 1 megahertz when we need to crank it up so that it can follow the LCLS2 rate. And of course, every single experiment is trying to look for something slightly different. So we want to create tools that the users can use to deploy their own models on these FPGA inference engines. So to finish up, we have new photon sources and new detectors that create more and more data. And that, of course, is the case for a lot of different science fields. And we're going to need new approaches to deal with the amount of data that we're generating. We demonstrated one of those techniques, which is we implemented a fast inference model on an FPGA that runs under 20 microseconds. And so we still have room to make something a little more complex. It's going to take a little more time, but give us a lot more answers about what's going on in the pulses. We hope to have customized AI for every experiment. And this concept is very transferable to other high data rate applications or applications that need very low power, because if we can do something very fast, we can also do it slower with lower power. So with that, thank you very much for your attention.
Thank you very much, Audrey. We'll now take some questions. And if you want to take a look at the Q&A, Audrey, I just posted in the chat the link so you can see the list of questions.
Right, just a second.
And Chloe, would you read out the top question?
Absolutely. So thank you so much for the great talk. And as of right now, our top rated question is, can you comment on the potential bias that the cookie box can introduce?
Bias in what way? I think, Ryan, you might be better placed for that one.
I mean, my impression would be the concern that most people have whenever we're saying we're going to use some sort of machine learning to pre-process data and throw away the raw. The cookie box probably would tend to, the current model would probably suppress very small features, I imagine. And I have a feeling that might have something to do with some of this confusion matrix piece. However, one of the things that is also key for actual implementation at LCLS2 is we will send raw data at a reduced rate. So every 100 shots or so, or maybe every 1,000 shots, we'll be sending raw so that we have sort of a monitor for this potential bias. And the iterative algorithm, the fairly complicated, extremely slow, painful thing that we do to reconstruct the X-ray pulse from this raw data, that's the thing we're training the neural network to solve the inverse problem. You know, that effectively shouldn't be susceptible to bias. Certainly not in the same way that the neural net would. So we'll be monitoring this sort of systematic error that might accumulate over time. Maybe that answers the question.
Yes, thank you.
Thanks, Ryan. Next question.
Sure. So our next question, our next top-rated question is, do you use something like Bayesian networks to quantify anomaly probability? How do you identify unknown anomalies with your network?
So currently the network does not quantify anomaly yet. It's something in our future work. So we're still exploring how exactly we're going to input that and how sensitive we're going to build it. So Bayesian networks are definitely something we're going to explore along with other things, but currently it doesn't do anomaly detection. It's just one of our very soon to be things that we're looking into.
I would say the only thing I would add to this is Bayesian networks are very interesting to look at, and general ensemble methods have got me very excited in particular. They don't fit well on an FPGA. The problem here is that when you do this in cloud, it's very simple to just iterate through a similar model with, say, stochastic weights or stochastic dropout or something. We can't do that, right? We have to fully parallelize everything and pipeline it through. So every inference that you're going to take some statistical distribution on has to happen in parallel. So they have to fit within the resources. And something that has been really keen on our mind is these neural networks eat up FPGA resources really fast. So doing these sort of ensemble methods or Bayesian neural nets is a little tricky on an FPGA. But that is sort of active research, I would say, not just in FPGA. We also are aware that there are new chips coming out. Certainly, those are particularly interesting from having increased resources for inference. Parallel multiple models running inference at the same time. That's kind of where we hope our solution might lie.
Thanks, Ryan. The next question I think is related to that too. The question is, given that you're trying to detect features in an image number of peaks, could a CNN be useful here?
Yeah, so if we're, in this case, it's not actually kind of an image right now, but we do plan on using it on images as well. So a CNN is great for images. However, it is extremely computationally expensive. So our latency is going to skyrocket because there's repetitive multiplications happening. So we want to do it, but this is gonna be further down the line when we start actually networking FPGAs together so that we can have larger networks happening faster. So right now CNNs could be useful, but they would need to be so small that they lose their usability for the current FPGAs that we're using. Of course, there are larger FPGAs, new chips that are coming up. So we're still keeping an eye on CNNs, especially when it comes the time to do the actual image detectors.
Yeah, the only thing I would add to that is we have to keep in mind that our data doesn't look like a real space image. It's this sinogram image. And so what you would normally think of as a simple, let's implement a CNN, doesn't sort of contain the physics that produces this sinogram. And in fact, the iterative algorithm to reconstruct the X-ray pulse is kind of like a CNN, but a sinogram respecting one. It takes sort of sine waves and says, how should I place these sine waves around this thing to ideally match the data? I would say, that is an interesting case. I think that's why Audrey, and initially we were thinking, oh, CNN might work for this. But in a weird, warped, and making that warping is kind of a high dimensional issue. And so that's why I think the fully connected feed-forward network was the initial thought. But yeah, I mean, it's certainly worth exploring. And for the individual detectors, that upstream FPGA that is inside the digitizer, that looks a whole lot like a convolutional brute force convolution because it's in an FPGA and that happens to be more efficient. But you're effectively doing when did the electron hit? And that certainly looks like a convolution. Not necessarily a neural network, but just a simple convolution or deconvolution.
Thank you, Ryan. We started a little bit late, so why don't we have one last question. This is from Kazu. He says, how do you make it, I think, work with higher rate for the future? Is it just increasing the allocation in the chip to the first layer?
So we have several different ideas to how we want to make it cope. So right now, the layer is too wide in the input. So we're actually looking into maybe using a recursive layer as the first layer that will, instead of spreading it horizontally, or using a split in the DSPs so that we can lower the latency for that one. In the other option, when we get some more complex networks for the images, for example, we're going to network some FPGAs together, which is a pretty complicated thing to do, but I think that might be where we need to be if we want to keep that low latency real-time aspect of it. But yes, definitely need to think about how we're going to increase that rate. And right now, the amount of nodes in a single layer is what slows us down the most.
Great. Thank you both very much.